There was a question during the break asking if set covering problem arises in other contexts as well. And the answer is sure, of course it does. In fact, the set covering problem had been long in existence prior to the method proposed for p-center solution. In general, the set covering problem is the following problem. You're trying, this is just side information on set covering because you encounter this all the time in solving min-max type of location problems. In general, in the set covering problem, you have a cost vector C, and you're trying to minimize the sum of the costs of xj's. In other words, this is summation cj xj over the j index, subject to, you have a matrix A consisting of zeros and ones, and you want each row of that matrix to be greater or equal 1. Okay, that's a vector of ones, and x is a 0, 1 vector here. So of, say, n components, or whatever many you have. Now, in the context we have, A matrix has as many rows as you have demands. In other words, it has n rows. Each row corresponds to a demand point. You've got how many columns? Q columns. Each column corresponds to a possible location, or a candidate location. So when you want to solve such problems, if the number of columns is too many, of course, problem becomes considerably more difficult, in which case you might want to think of generating them as you need them. And in our context, the number of columns is considerably larger, substantially larger than the number of rows of matrix A. But if you are looking at the vertex restricted version of the problem, in that case, of course, the candidate points will come from vertices as well. So we're talking about a square matrix in that case, which is easy. I think some of you mentioned the problem by Mustafa Pınar. That one is on weighted vertex restricted problem. So it's pretty obvious, actually, that paper doesn't seem to propose anything new to me. But maybe the computational experience is good. Maybe. So I really do not know what the exact contribution of that paper might be. Okay, so now where does this problem arise? Well, as the name suggests, it arises when you have a set, a mother set, so to speak, and if you have certain subsets of that set, and if you want to pick the smallest number of subsets so that the union of them will give you the mother set, that's the context where the problem arises. So you have some set, and then you have, say, L subsets of it, and you want to pick the minimum number of subsets, say K, so that the union of the subsets for the picked set, K is a subset of the index set of the subsets, gives you S. That's the problem. It's a combinatorial problem. And how do you turn that into a set covering problem? Well, all you do is you define a 0, 1 variable xj for each sj. Xj is 1 if you pick the jth subset. It's 0 if you don't. So when you do that, so j is in the picked set, 0 if not. So all you have to do in that case is additionally define aij. What is aij in that case? Aij will be 1 or 0. When will it be 1? If subset
J covers element I.
element I, yes. If Sj covers the ith element of S, meaning that the ith element is actually also an element of Sj. Assuming that the set consists of these elements. Say T of them, whatever, okay? Small si is the ith element of set S. So in that case, when you do that, of course, if there's a cost associated with choosing the jth subset, that cost would be Cj. That cost could be, for example, the number of elements in subset Sj, or whatever. People define these costs differently. Nevertheless, you're trying to minimize this. How many did I have? L, subject to summation aij xj is greater or equal to 1, j going from 1 to L, and this is for each I 1 up to T. We have the same structure. Now, where does that arise? Well, it may arise in various ways, actually. For example, anybody thinking of an example? Suppose you have districts around Ankara, and you have schools, and each district has, say, primary school kids, a certain number of them, and you have so many schools, and you want to convert some of these schools to primary schools, so you want to be able to cover the entire set of students at the primary level. In that case, you would be solving a set covering problem. It has nothing to do with location. Okay? All right, so these are all possibilities. In our context, let me just say a few more words here. In our context, the set to be covered is the set of vertices. These are the vertex numbers, 1 up to n. Things that cover are the candidate locations, y1, y2, etc. Okay? Now, y1 for a given r value may cover certain vertices here. So I just put an arc to indicate that y1 covers those vertices that are connected to y1 by an edge. Okay? Likewise, y2 covers maybe a bunch of them. Yn covers a bunch of them. So there's an edge exists if the distance, in our case, vi, yj, the weighted distance, is less than or equal to r. That's the way we define our bipartite graph here. This is a bipartite graph because the node set is in two parts, the first one and the second part, and all the arcs go from one side to the other one. That's called a bipartite graph. So in our context, you actually declare aij equal to 1 for each arc. That's what you're doing. And for the missing arcs, you declare an aij value of 0. So where are the sets here? The subsets. I mean, the set is quite okay. Yes, somebody?
Like yi, that are connected to yi is the
Okay. So S1 is the set of the vertices vi such that arc vi y1 is defined. That's what you're saying, right? Okay. Yeah. The set of vertices that are directly connected to y1 constitutes the first subset. The second one is defined similarly, so on and so forth. So that's the contextual relationship between what's going on here and the set covering problem. There are certain heuristic rules that really help with set covering problem solution. Let me give them to you. One is called the row infeasibility rule. If row k of the A matrix so if row k of A has all zeros, what do you conclude? There's no feasible solution, because regardless of what you do, you cannot cover that. Now, there's another rule, row feasibility rule. If for some row R and column C there is exactly one in position in position C in row R, what's the conclusion? You have to choose that particular x value. In other words, make xc equal 1. Otherwise, you don't have a feasible solution. It has to be. It's implied. Okay? Okay. Row dominance rule. if there are two rows R and Q, such that, of course, R is different from Q, such that the number of ones in row R is a subset of the number of ones in row Q. Well, actually, it's not the number, but the set of ones in row R, the set of positions of ones in row R, let's just write it this way. Position indices of ones in row R is a subset of those of row Q. Then, of course, one row dominates the other one. In other words, one of them can be eliminated. Which one? R. Are you sure?
The subset. If it was columns,
Which one can be dropped? That's what I'm asking. Q? Yeah. But he's saying row R. Are you sure?
If it was column, then it would be R.
No, we're talking about rows. So you have one row, in this case, row R. The positions for ones in R is a subset of positions of ones in row Q, for example, like this. Why do I drop row Q in this case?
Because by satisfying R, we will also be satisfying.
Yes. Okay. So row Q can be dropped. Okay. It's hard to write it there. Took a long time to write it. Column dominance rule. If for two columns B and T, the set of positions of ones in column T is a subset of that of column B, and if the cost associated with variable B or column B is not larger than the cost of T, then there will be at least one optimum solution where xt is 0.
Why some optimal solution? Why not all optimal solutions? Because if this
Not necessarily, none. Well, it doesn't have to. This is only for domination. There could be, you can't say that. You can't say that in all optimal solutions you are going to have that. There could be alternate optimal solutions where you would have the same cost. But it would surely be wise in such a way, in such a case, that since the cost of column B is less than or equal to CT, and since B covers actually more elements of the demand set than the other one, of course, you can just get rid of column T or set it equal to 0. Okay? Let me give you an example, A matrix, and let's see what we are going to do. Actually, let me go column-wise. It's easier. That's the first column, the second column. That's a small matrix, but it takes a long time to write it down. Do we have any row infeasibility? No. How about row feasibility? Any row dominance? What do we want? We want the set of positions of ones in row R to be a subset of those of row Q.
6 and 7, 5 and 6.
Row dominance. Actually, I've got 2 and 3. 2 dominates 3. Is that true? Okay. So we drop 3 in this case. And then once you have that, 4 and 5.
No, 6.
I've got also 4 and 5.
Yeah. Do we choose these arbitrarily or?
No, I'm just going sequentially, actually. You compare 1 and 2, 1 and 3, 1 and 4, so on and so forth, except that when we do this by inspection, we don't go like that.
No, I mean,
I'm going down the list.
we have both 4 and 6 dominating 5, but 6, let's say, dominates 5 less, no, more strongly because.
Yeah, but I see what you're saying, but I'm not paying.
Arbitrarily or?
You can choose them at any order you wish, because as soon as you identify a dominance, one of them goes away anyway. So, for example, 4 and 5, 4 dominates 5, so you drop 5 out.
And 6 dominates 4.
Okay, but let me put them in order. 6 dominates 4. Okay, so you drop 4. Okay.
6 also dominates
7. What else?
8 and 9 are the same.
If they are the same, we can delete one of them, 8 and 9. So out of 8 and 9, let's delete, for example, 9.
And 10 goes because 8 also dominates 10.
Okay. So 8 also dominates 10. That's what you're saying. Okay. Any others? No, it has more.
More ones.
The one that has more ones is dominated. Isn't that what we said here? If there are 2 rows R and Q such that the set of positions of ones in row R is a subset of those of row Q, then the one with more goes away. Okay? Why? Because in an attempt to... Okay, why?
Because by satisfying the less, you lost satisfy the more.
True, true. As soon as you try to cover the one that survives, you actually also cover the other one automatically. Okay, that's why. All right, so that's row dominance, and then we have column dominance. 1 dominates 2. One. Yeah, so in that case, yeah, we don't have to pay attention to the costs. Yeah.
Now you can get the restricted.
Pardon?
Argument
Yeah, actually, this is the restricted version of the set covering problem. I mean the P-center problem. But actually, I picked a matrix, which sort of was arbitrary. Yeah.
I mean, when we look for column dominance, are we looking at all the matrix or the one that we reduced? No, we don't have.
The one that we already reduced, yes. Of course, it helps. All right. I have 1 dominating 2. Why is that true? Because if you disregard the ones that are already crossed out, in that case, 1 dominates 2 because you have more vertices covered here than number 2 covers. Okay, so you can set x2 equal to 0, which means you just get rid of that. Okay. What else? 1 dominates 3 as well. Does that? Okay. 5 dominates 4.
And also 6.
And 5 dominates 6. I don't have that.
Look at column dominance 2B, just look at the remaining ones and zeros, or
Yes.
A5 remaining.
The remaining ones, yeah. He asked that question at that time. I guess you might have missed that. But yeah, we just delete the ones that are crossed, and whatever remains, we work with that. All right, I don't have 6 dominating 4.
No,
Do you have that?
6.
5 dominates 6? Why did I miss that one? 5 dominates 6. Yeah. Okay. Before that, I have 7 dominating 6. Well, 6 is already gone.
7 dominates. 8 dominates 7.
8 dominates 7. Are you sure? 1 dominates 10, 8, and 9. That's what I have. Is that true?
5 also dominates 7.
8, 9, and 10. Yeah. I guess these are all gone. And 5 dominates 7.
The remaining indices are the same.
So we have a rather small matrix left. Let me see. We have 1 and 5 surviving. And we have 1, 2, 6, 8. Where is 5? 0, 0, 1, 1.
Do we apply row dominance again to this one?
Yes.
Can we delete 1?
Yes. You could now. You can go back to the row dominance again.
8 goes and 1 goes.
Which dominates which?
8 goes. 6 dominates 8.
6 dominates 8. Row dominance. So 8 goes.
And 1 and 2 dominate each other, so 1 of them will go as well.
Okay. So x1 equals 1, x5 equals 1 also. That's it. Of course, this was a lucky choice.
We need to apply the last row dominance then, because we already know 1 and 5 is going to be 1.
Well, actually, this is partitioned now. In other words, you have exactly 1, 1 in the remaining case. I don't know if I'm answering your question, but this is what we've got. There's exactly 1, 1, so it has to be 1. The other one also has exactly.
Care of the assignment, that's right.
Yeah, so that's essential. Yeah. Yes.
Why do you call these rules heuristic rules?
Well, heuristic rules, well, they are good rules, but they give you a solution. Well, it doesn't give you a solution. It reduces the matrix. So it doesn't get you to an exact solution all the time. In this case, it turned out into an exact solution. It simply simplifies the problem, actually.
Also, you cannot apply them exactly.
Yeah, there are, yeah.
Might be so, well, might be so.
If you're able to apply them, it depends on, what you apply depends on what you have so far applied. Whether or not there's whether or not these are order invariant, I'm not sure. They may be actually order invariant. Okay, regardless of in which order you apply them, you may end up with the same matrix. But I'm not sure about that, so don't take my word for that. To me, it looks like to be the case. You might want to try that and see. Okay, anyway, that's enough for set covering. What I'm going to do is, next time, I'm not going to continue any further today because some of you guys have exam and I don't want you to, too much, load you too much with this. I'm going to let you early, but next time we're going to start talking about tree network problems, and there's a very complicated algorithm by Karive and Hakimi. I'm not sure if I want to cover that. It's a real, very messy algorithm. Well, it's not, I shouldn't say that. The camera is capturing all I'm saying now. But it's mostly computer-oriented stuff rather than, some theory-oriented stuff. Nevertheless, if I have the patience, I'll go through that, and you'll see what kind of a polynomial algorithm we have for the p-median problem on tree networks. There's an easier one later on developed by Tamir. I'll probably go through that. And the p-centered problem on tree networks, I will also cover that. Okay, so much is enough for today, okay, because we have exam.